we can make a start on Grover's algorithm. This might be the last topic that we do, depending on whether you guys want to do a revision lecture. So obviously on Thursday, we'll have our very last lecture. So we can reserve that for doing some revision on some topics that you guys might want to go through, or of course we can keep on going with the material. I've still got a few sort of slides sets left, but maybe we can get through a lot of this one today. So basically this is another quantum algorithm. It's Grover's algorithm. It's one of the most famous quantum algorithms.
Sorry, Professor.
Oh, sorry. Yeah.
A question. I mean, not a question, but like, could we have the solutions for homework like before?
Oh, sure. Yes. Yeah. So I'll get you back the marked solutions as soon as possible, so that you'll have that ready for your finals. Yeah.
And also, like, is it possible for us to have like some kind of like the exam from the past years?
Okay. All right. Sure. Yeah. I'll upload something like that. Yeah. For one of the past years, I think should be kind of similar material. So yeah.
Thank you.
But I mean, I think you've seen already basically what the exam will be. I mean, just based on the midterm, it will be similar style to that. So you can
just for like wanted
yeah.
some practice for like the kind of questions that we studied like
Sure.
after
Sure.
the midterm.
Sure, of course. Yeah.
Thank
Okay.
you.
All right. Yeah. So this Grover's algorithm is, like I said, one of the famous quantum algorithms that are sort of known. There's not, unlike sort of classical computer algorithms, there's not like, sort of so many algorithms that are, useful, that actually shows you a speed up over classical computers. But Grover's algorithm is one of them, and it's very useful. So this picture that we've got here, as what I'll try to see, this is like the basic task of Grover's algorithm, which is to kind of find a needle in a haystack. So this English expression, needle in a haystack, it's like trying to find something which is very hard, because of course a haystack is very big and needle is very small, and also needle kind of looks like hay, so it's very difficult to find. So finding the needle in the haystack is basically the aim of Grover's algorithm. So just to give you a bit more background on Grover's algorithm, well, this is Mr. Grover here, is an Indian guy, and this was, as I said, one of the first famous quantum algorithms. Deutsch's algorithm is like perhaps the first quantum algorithm that shows a quantum speed up, but as we've kind of discussed, they're not particularly useful algorithms. You can't really use Deutsch's algorithm for anything except for a kind of a demonstration to show that it's possible to actually do something faster with a quantum computer. But Grover's algorithm is actually something that is potentially extremely useful. So it shows a quantum speed up. So I would say that maybe if you were to name the two most famous quantum algorithm, they would be, Grover's algorithm would be one of them, and perhaps the most famous quantum algorithm is Shor's algorithm. And I don't think we're not really going to have the time to do this one, because Shor's algorithm is a little bit more complicated than some of these other algorithms. But the task that Shor's algorithm achieves is to find factors of a number. So if it's like you're given the number 21, the algorithm would be able to find that, you know, the factors of 21 are equal to 7 times 3. So it gives the factors. And it can do this exponentially faster than the best known classical algorithm. So it's quite a spectacular example of a quantum algorithm. So Grover's algorithm, as I'll show you, is a kind of a search algorithm. And actually, it's also provably faster. So this Shor's algorithm is like exponentially faster than the best known classical algorithm. You know, there might be a faster way to factor numbers, like a classical algorithm, that is actually faster than you know, something that takes exponential in time. You know, but it's just that the best known one is actually there's an exponential difference. Whereas with Grover's algorithm, actually we know for sure that the quantum algorithm is faster than the classical one. Okay. So it was originally shown in this paper, 1996. So what is it? So this is the kind of problem that we're talking about. So suppose we have the task that we want to search a large database and it has like n entries in it. Okay, so an example would be like what I've got just down here. Here I've got, you know, sort of a database. It's got, you know, names of people and their addresses, and then the city that they live in, the license number of their car. Oh, sorry, maybe their driver's license. Yeah, and well, they're just numbered from one, you know, one to some number 14 here. And what we want to do is to kind of search through this database. So that's the kind of task. And if we were trying to search by name, of course, this is you know, not such a hard problem. So if I were to say, you know, okay, I want to find the guy that's called like Evans, right? Now, of course, these names are ordered alphabetically. And so even if this database contained like, you know, 1 billion names or something like that, it wouldn't take you very long to find the name because, of course, you know, you can just search for it alphabetically. So we have some convention, you know, alphabetical order. And actually, even though there's, you know, a huge number of names in there, you can quickly find it because, you know, it's all ordered, right? And so you can easily find each entry. But if the database isn't sorted, then it's not as easy to find, right? So if I were to instead say, okay, you know, find me the entry where the license number is, you know, ends like say in the four digits of you know, 0220. Because these license numbers are not ordered, basically, well, not basically, you know, actually what you have to do is to just go through and check each one because there's no ordering or anything like that. You have to look at each number. So you're looking for 0220. So it's like, no. And you go, okay, this one, number 13. You basically have to look through the whole database, and okay, you might get lucky. It might be in the first half, but well, in this case, it was in the second to last. So you ended up looking through almost the entire database before you found it, and there's not really any other way of doing it. Like in an unsorted database, there's just no strategy that you can use because, you know, the ordering of all these things are kind of random. And so, you know, if you were just to do this randomly, this had n entries. On average, it's going to take, well, n over 2, right? Because sometimes you get lucky, sometimes it's, you know, you're a bit unlucky, and then, you know, on average, it might be something like n over 2. We normally don't really care about the this kind of n over 2. So the important thing is that we say that it scales with n, which is the number of database entries. Okay, so forget about the proportionality factor, just say how it scales with n. So in computer science, kind of way of saying it would be that the complexity of this is order n. Okay, so the way that we're gonna so let's kind of abstractify this problem a little bit. So let's say that the instead of having this kind of database that we have here, we're going to work instead with what's called the oracle. So the oracle, we already heard something like this in the previous slides, kind of, for example, in the Deutsch's algorithm, we also talked about an oracle. So basically the oracle is, instead of having this kind of database with numbers and names and stuff, let's just have a function that you have, ones and zeros as the output. X is the index. Okay, so say here we've got the index number. So we're just going to label each of these entries by a number like this. And then f of x is basically something that tells you whether that's a solution or, that's basically just a marker just to say whether this is the thing that you're looking for or it's not the thing that you're looking for. Okay, so for example, over here, maybe this function here could be something like, and it totally depends on the question, of course. So here, it might be something like, I want to find all the people where, say the last digit is 6 or something like that. So in that case, if you're looking at the last digit, then here's one with 6, here's another one with 6, and then all the other ones don't have 6. So it's number 2 and 4 are the ones that we're going to be looking for. So in this case, okay, for this example, I have like number 3 and number 9 are the ones that we're looking for. And whatever it is, the thing that we're kind of trying to search within. So basically, f of x is just a thing, just points out solution. And then what we're trying to do here is, of course, find which ones are the solutions, right? So, the aim here is like, okay, you want to find, okay, which of the people with 6 as the last digit in their license number. So the answer is 2 and 4. Okay. So in this case, basically what we're trying to do here is to find this, the solution of this. So basically, f inverse 1, which are the solution cases, we're trying to find all the cases where f of inverse is 1. Okay. So we can treat this, think of the oracle again as some black box. We don't have to really think about like what's inside the black box, even though, well, you could always think of a circuit that does this. And so usually what the situation that you have here is that finding this inverse is kind of a pretty hard problem. Okay, so it's easy enough to just plug in x and then find f of x, but if you were to say which ones of the f of x's are 1, well, basically this is again a search problem, because the only way that you can really find this in general is to look through all these cases and then find the ones where the answer is 1. Okay, so you have to look through all these ones and then you say, okay, fine, 3 and 9 satisfy this equation here. So usually this kind of oracle, it's sort of easy to go forwards, but then it's kind of hard to go backwards. So this is a kind of a pretty common setup. And in fact, this is often what's used in cryptography and things like this, because you have these sort of one-way functions where it's easy to calculate one way, but hard to go the other way. Okay, so we're going to work with this kind of oracle function. And what we're going to do is we're going to allow this oracle to be like a quantum oracle. Okay, so that basically means that we're going to allow it so that the input of the oracle can be in like a superposition state. So you've got, this is the input state. So we're going to have basically the same kind of setup as we already saw in Deutsch's algorithm. And so remember, in Deutsch's algorithm, we couldn't just have like a oracle that just directly does something like this, where you have x, and then you have the oracle, which is contains the function x, and we couldn't do something like this, basically because this was not a unitary process, right? So imagine if you get the value 0 over here. Well, there's lots and lots of cases that actually give 0, right? And then if you found the output to be in, well, I should really say 0 state. So if you found the output to be in 0 state, there's no way that you could figure out in general which one was the input state. So this way is basically, it's not an invertible function, so we can't implement that with quantum mechanics. Okay, so that's why we eventually went with this type of circuit on the next page, because this is an invertible kind of way of implementing this oracle. So we, instead of having the output as just f of x, we have the output as just adding modulo 2 f of x, and where in this case f of x is like this type of function, and then we just add that into the y. Okay, and so basically what this is going to do, it's going to flip if f of x is 1, which is like one of these solutions here, it's going to flip the output of this one, so it's going to be y plus 1, and then modulo 2. So if this y was 1, then if this was 1, then if f of x is 1, then this would become 0, and if y was 0, then y plus 1 would be 1. So we basically same setup as Deutsch's algorithm, if you remember how that is. Okay, so that's how we're going to implement the quantum version. And then remember that also in the Deutsch's algorithm, what we did was eventually we prepared this input state here to be a minus sign. Okay, and then if you just recall what happened with Deutsch's algorithm, what basically that eventually does is, if you start with this state x, then it will output the state again x, but then with a -1 phase here. And so actually, because nothing really happens to this lower part of the circuit, we can just kind of omit it, or just well, yeah, just don't show it in the notation. And so what we're going to actually use is something like this, where basically x becomes -1 to the power of f of x. And that's basically what we're going to consider to be our oracle. Now, I think I said this for the Deutsch's algorithm as well, but to me, like, this whole thing with the circuit and, putting the minus state in and all this, actually, it's sort of a historical thing. So if you find this whole thing with the UFF and the, this putting the minus state in, if you find that whole confusing, actually, instead, what you can, I think it's just, basically the same thing, is to just say that, okay, we're going to implement the oracle using this kind of formulation, where basically the input state is x, and then the output state is -1 to the f of x. And if you just say that that's going to be my definition of the oracle, well, this is a perfectly unitary transform, as you can see here, because if you start with this state here, you can easily just apply this one twice and then go back to the initial state. So this is perfectly unitary transform. So if you just say that, okay, that's my oracle and that's the end of the story and that's how I implement it, then you don't have to worry about all this kind of stuff which happened, which I consider a sort of a historical, historical origins of this thing. You can immediately jump to this if you prefer that explanation. So long story short, basically we're going to implement the oracle according to this kind of operator. So we have O as an operator here, gets applied to X, which is, again, it's the state form of basically all these database entries. So it's just the index of all the different cases. And basically when the oracle gets applied to the state X, it has a plus or minus one phase. And so it has a plus one phase if it's not a solution, and then it has a minus one phase if it is a solution. Okay, makes sense. Okay, hope so. All right, so so that's the oracle. Basically, we're going to encode, this box here as something that puts a -1 phase on the states. Now, what we're going to actually also need is another very similar type of operator, and this thing doesn't have a really good name, but I'm going to call it the phase inversion operator. Okay, and it does just about the same thing. In fact, it's even simpler than the oracle. Basically, what this thing does, what I'm calling V0 here, is it puts a minus sign if this state is 0. And so, by the way, when I say X is equal to 0, what I sort of mean by that, and notice I've got like multiple lines here. So for example, in this 3-qubit case, when I say X, what I actually mean is like the binary form of X. Okay, so basically in this 3-qubit case, you can have X going from 0 to 7, because there's 3 qubits, and 2 to the power of 3 is 8. If you start at 0, then it goes to 7. Okay, and then so basically, when I say state, say 0, 1, 2, 3, what that actually means in terms of qubits, basically the qubit decomposition here is, for example, this would be 0, 0, 1, 0, 0, 0, this would be 0, 0, 1, dot, 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 1, 1, 1. Okay, so that's actually what I mean when I say state X. It's actually like a multiple qubit state. Okay, and when I say X equals 0, what I mean by that is that basically it's the 3-qubit state in this case with all the qubits 0. Okay, and basically what this particular operator V0 does is to put a minus sign on the state, just the 0, 0, 0 state, and then all the other states are left alone. So there's no minus state, -1 phase in front of all the other states here. So this is the only one that gets the -1. So for example, okay, here's a 2-qubit example. So given an arbitrary superposition state of 2 qubits here, 0, 0, 0, 1, 1, 0, 1, 1. Basically what V0 does is just to flip the flip the sign of the 0, 0 state. So there's a minus sign. Okay. Now, so that's V0. Now let's do one more extra step on this, and this will be the actual operator that we use. Now, if I put Hadamard gates on the start and the end of all these, basically what this does is to rotate the whole basis from the 0 state to the plus minus basis. And so actually this orange V this V operator, which I'm going to define as this thing where I've got these Hadamard gates beginning and ending. Basically, what that does is something very similar to here, except that I'm working not in the 0, 1 basis, but in the plus minus basis. And because when you do Hadamard of 0 state, you'll get that's equal to plus. So basically, this state here, where x equals 0, and that basically actually means the state which is 0, 0, 0. Basically, instead of the 0 state picking up the minus phase, actually the state that we'll pick up is the state where all these are pluses. So basically, the only state that this will pick up a minus state, minus 1 phase, sorry, is this state where all the states are plus. Okay, so on every qubit, if every state is plus, then it will pick up a minus state. Now these other states, what do I mean by the other states? Just like I've had over here, the other states are just all the other combinations. So here's x in the plus minus basis. So when I say 0, 1 to 7, what I mean in terms of the states here is that this first one will be the state plus plus plus. Second one will be the state plus plus minus. And then dot dot dot. The last state is minus minus minus. Okay. So in the qubit representation. So basically, this state here, state plus plus plus, is the only state that actually picks up a minus sign. Okay, so that's basically what the V operator does. It just applies a minus sign on the state plus plus plus. Okay. Is that fine for everybody?
Yes.
Okay, great. Okay, so now we can introduce Grover's algorithm, okay? And so it's actually looks pretty simple in terms of the actual algorithm. So this is the quantum circuit for it. And what is happening is that, okay, so the initial state is just the 0 state, okay? And then you initially apply some Hadamards, okay? So at this point here, the state will actually be the state just plus plus plus. Okay? So over here, we're going to go through this, I think, in detail, but over here it's plus plus plus. Okay? And then after that, we just apply the O and the V operators. Remember, this O is the oracle, so that's the thing that applies the minus signs to the solution states. Then V is just the operator that applies the minus sign just to the plus state, okay? So actually this state here. And then you just repeat this. So you just repeat this OV, 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 OV for a bunch of times. And there's some optimal number of times to apply this. And that depends upon basically the size of the database, that's N. And also depends upon how many solutions there are. So for example, in the example that I had before, okay, how do I go back? I'll go back. Oh, here we go. Okay, yeah, in the case that I had before, this M in this case, so for example, just to tell you what the N and the M is here is, so N in this case would be, for example, 12. Yeah, that's the number of database elements. And then M would be the number of solutions, and that would be 2. So that basically specifies the, these are kind of 2 parameters that you have. And let me just delete that. And then so you want to apply this pair of operators, O and V, for a number of times, which is n over m square root. Okay. And then once you've done that, you measure the qubits. And if you do that, when you measure it, basically the output of the circuit should be one of the solution states. Okay, so you just read off the solution state. So perhaps the solution state is say it's that state. So whatever that is in binary, you just read off the values. Okay, so that's how it works. Now, I'm sure this looks kind of mysterious. Why does this work? So let's dive into that. So let's go through it step by step. So as I just said, after the Hadamard gates, basically what you'll have is this state where you've got Hadamard applied on these 0 states, and that produces the plus state. Okay. And so here's a plus state, here's a plus state, here's a plus state. Now, if you expand all this, so you can write it like that, that's perfectly fine. But another way to think of it actually is if you expand all these brackets here, then what you're going to find is that, well, you'll have actually every single possible combination of states. Okay, so you'll have every state here going from 0, 0, 0, 0, 0, 0, all the way up to 1, 1, 1, 1. So actually this state plus 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 is actually an equal superposition state of all the potential different database entries. So basically it's like, in this table here, you're starting off with a superposition of every possible entry. Okay. And we don't know which ones are the solutions yet. So in this case, it's like 3 and 9. But the starting state is just a superposition state of all. Okay. Oops, too far. All right. So that's the first step. Okay. Now let's look at what happens when you apply this oracle state once. Okay. So remember what the oracle does is to just apply a minus sign on the solution states. Okay. So so for example here, we're starting with all the possible potential solutions. Yeah. And basically what it does is it's going to flip after this first oracle here, going to flip the sign of one of these. So imagine if like this guy 0, 0, 0, 0, 0, 1 is, say, this one of the solutions. It's going to flip that sign to a minus, and there's only one solution to the whole database, then that's the only term that gets flipped. But if there's more than one solution, then there will be multiple spin flips. So maybe like this last one is also a solution. In that case, that will also have a minus sign. All the other ones that are not solutions will remain the same in the phase. Okay, just have a plus phase. So the way to write this more generally is like this. So suppose we have here the set of all the states that are like not the solution, right? So all the cases that do not satisfy fx equals to 1. This is basically, this part of it is like fx is not equal to 1, or of course it's 0. So these are all the x cases that satisfy that. And here are all the cases that do satisfy that. So this is fx is equal to 1. Okay. Okay, and so that we actually can normalize the state, here's the normalization factor. Well, the number of cases that are not in the solution, well, n is the total database size, and m is the number of solutions. So obviously, the number of not solutions is like n minus m. Okay, so this is why the normalization factor is like this. Over here, the number of solutions is just m. That's how we defined m. So the normalization factor is 1 over square root of m. Okay. And so it's actually what we're going to find is that actually writing it in terms of this state, which is like the sum of all the states that are not a solution, or the sum of the states which are a solution, this is actually quite a good way to write it. So what we're going to do is let's just go back to this point in the circuit. Okay, so let's write this initial state, which is the state which is a superposition of all the possible states. Let's write it in terms of these two vectors here. So the x not solution and the x solution. Now, just with a little bit of rearranging, if we multiply this by square root of n minus m, then we're going to get, well, the sum of x. So x in not solution. So this will be equal to square root of n minus m. I've just rearranged this equation where it's x not. Okay, I'm just going to call it x not. And then over here, this is the sum of states that are in the solution. So this one, what we can do is we can, this one is going to be called multiplied by square root of m. Let's just put this on the other side. So these are the solution states. Okay. And then if we, wait a minute. Oh yeah, so that's right. Okay, and then because this state here actually has this normalization of 1 over square root of n, so what we can do is, this stuff here is actually equal to basically the sum of these two guys here. So if we add basically these two states here, that's the inside of the brackets. And then if we just substitute this guy into here, and then this guy into here, then we're going to get basically, this is the equivalent way to write this state, which is the initial plus state. So remember, this is the state just before the oracle. Okay. And if we write it like in this form, makes our calculations quite easy, because so everybody fine? I'm going to erase this now. Is that fine? Yep. Okay. All right. So if we write it in this form, and it's easy to see what the oracle does, because when we apply oracle to this initial plus state, then remember what the oracle does is to add a minus sign to all the solution states. Okay. So it's just going to flip this sign. So just to emphasize what has changed here, here's the plus sign over here. That's the state before the oracle, and state after the oracle has a minus sign. Okay. So that's what happens after the first step. And well, in general, basically, that's what the oracle always does. Just flip the sign of this this term here. Okay. Then let's keep going. And then now, oh, I see. Yes, sorry. There's a really nice way to actually visualize what's happening here. And let's plot this state, this general state here. So actually in the first step, we've got particular coefficients of n minus m over n root and m over n root. But let's just look at this more general case first and just try and get a sense of understanding of what this oracle is actually doing. So what it's actually doing is, of course, so it's flipping the sign of this b, but we can visualize this geometrically because, so this original state here, which is a and b, so some arbitrary coefficients, and the axes here, let's consider these. Here's the x not sol state, and here's the x sol state. Okay, so what O basically does is to reflect around this x not sol axis. Okay, so because after you apply this oracle, this has a minus sign, so whatever it was up here, it will be reflected by this, around this axis. And so I'm kind of thinking like a and b are real numbers here, and in fact what we're going to see is that actually throughout this whole thing, the coefficients of a and b are just always real numbers. So we don't really have to think about imaginary components of a and b. So it makes our life a bit easier. So we know it's definitely a reflection because basically, here, the coordinate here is, a, and the coordinate here is b. And of course, the coordinate here is minus b. Coordinate here is still a, of course. And so obviously it's a reflection. So, this angle here is the same angle. So this is a really neat way of visualizing it, and we're going to make use of this because we can actually use the same trick to understand basically what the other operator here, v, actually does. Okay, so remember O and V are just about the same thing. I mean, well, they're not the same thing, but they're very similar operators in the sense that O is something that adds a minus sign to the solution states, and then V is the operator that adds a minus sign to the plus state. Okay, so all these states plus. So kind of they're just sort of similar kind of things. So we can actually understand what the V operator does because basically if you think about O as basically performing a reflection around about the this state that does not have the solution. Okay, so because V is something that actually okay, maybe it would have been clearer if I actually put the minus sign. So over here, okay, it might have been a bit clearer. It's actually the same thing, but it might have been a little bit clearer if I defined this in the opposite way in hindsight. But so because V is the operator that applies a minus sign to the plus state, we can also visualize V as being a reflection around the plus state, actually. Okay, so basically the role of the plus state is playing the role of the not solution state that we had for the oracle. Okay, so in the case of the oracle, we were doing a reflection around not sol, and for V, we're performing a reflection around the plus state. Okay. I mean, you can show this mathematically, but it's a little bit tedious because it's actually, around these green axes, and the green axes are not, it's not the same angle as the as the red axis. Okay, so I remember when I was trying to, write these slides, I tried to also do it mathematically, and then it just looked very confusing. And I think this is actually a much clearer way to explain it, that the action of the V operator is just to reflect around this plus state. Okay, so I hope you can just sort of see that, because basically the V operator and the O operator are, very, very kind of similar types of things. Okay, now actually, just with the knowledge of these two things, we can actually already deduce basically what's going to happen in this whole circuit. So we don't have to really continue further in this whole sequence. Of course, if you try to do this algebraically, it will start to get kind of messy. So, so let's look at basically what happens after applying, firstly, just a single pair of this O and the V. Okay. So let's first look at this picture, because it's probably the easiest thing. So basically, we've got kind of like these two pairs of axes, where the red ones is the solution and not solution, and then the green one is this plus state, and then the state which is orthogonal to this plus state, but in this two-dimensional space. Okay. So so those vectors are fixed. So think of them as just like the two sort of coordinate systems. Okay, so there's the red coordinate system and then the green one. Okay, these black vectors are going to be like the state that evolves during the sequence of this algorithm. Okay, so the initial state is going to be along this diagonal green vector, because as I said here, the state here is the state that's all plus. Okay, so here's the initial state at this position. Okay, now after the first O, what's going to happen is that it's going to end up down here. Okay, it's going to end up beneath the red axis. And remember, the whole thing that we're trying to do here is actually to swing this vector actually towards this state here, x sol, because once we've found this x sol, that's basically what we're trying to do in this whole algorithm. We're trying to get the state in this quantum computer to swing towards this state x sol. Okay, so actually in the first step, it actually goes the wrong way. Okay, so after doing O, it's actually going the wrong way. It's actually further from x sol than it was initially. Okay, but when you apply the V, and remember what this does is to then perform a reflection, not around the red axis here, but around this green axis here. Okay, so after the first O, it's down here, but after the first V, it actually gets reflected this way. And this time, actually, it ends up being closer to the x sol than it started with. Okay, so basically, this pair of operations, O and then V, will actually swing this vector closer to this x sol vector than it was initially. Now, if you repeat this, you can actually figure out what's going to happen. Okay, because let me use maybe a different color here. So now the vector's here, right? Okay, and then so we're at this point in the circle. Okay, so after one iteration of OV, the vector is here. The next O is going to reflect this blue vector here around the red axis. Okay, and so this angle here is going to be 3 theta over 2. So actually, it's going to end up over here. And this angle here is going to be 3 theta over 2. Okay. And then this V here is going to reflect this blue vector around, now this time this axis. And if you look at the, hold on, did I do this right? No, I did it wrong, sorry. Let me try and fix it up. Okay, so sorry, this is where we start at this point. And then the angle from here to here is 3 theta over 2. So actually the angle from here to here is 3 theta over 2. Okay. Then now we're gonna, the second V here is going to reflect this blue vector around this time this green axis here. And then the angle from here to here is actually 2 theta now, okay? Because it's 3 theta over 2 between the blue vector and this red axis. And then this angle here is theta over 2, so that's 2 theta. So actually where this will end up after the second V is actually going to be over here. And from here to here it's 2 theta. And then from here to here it's going to be also 2 theta. Okay. So if we track what's happening to this vector, so in the first, let's look at the angles. So in the initial state, the angle was theta over 2, and then over here the angle was 3 theta over 2, and then over here the angle is 5 theta over 2. Okay, so basically each time you apply this OV, it gets closer and closer to this X sol. Actually, if you keep on doing this, it can overshoot. Okay, so if you're wondering, what happens when it finally actually gets there, and then you keep on applying OV. Actually, it'll just keep on going. So actually, it'll just keep on revolving like this. So this is why you need to actually stop and then measure when you actually applied it enough times. Okay, so I'm going to explain the maths now, but basically that's really what's happened. Any questions you guys have? Okay, well, stop me if anything is confusing. So mathematically, this is how we kind of derive it. So remember these factors of square root of n minus m n and square root of m n, that those appeared, I think, when we first wrote this plus state here. So remember the plus state, we wrote it with these factors here. So actually it's nice to just define our angles in terms of these values. Okay, so we're going to call this thing cosine theta over 2 and this thing sine theta over 2. Now, of course, sine squared plus cosine squared should be equal to 1. So if you work that out for these things, you'll find that it is in fact equal to 1. So the initial state that we start with, so this is this point in the circuit, we can, using this definition of theta, we can define it like this. Okay, so cosine theta over 2 and then sine theta over 2. All right, and basically using this kind of geometric argument, after one step of the VO pair, so VOV, then basically it starts here. This is where it starts, and this is where it ends up. So basically, this angle from the red axis is 3 theta over 2. 3 theta over 2. So this angle here is now going to be cosine 3 theta over 2. This is sine theta 3 theta over 2. And as I sort of kind of argued the next one is going to be 5 theta over 2. So in general, after k applications of this VO, you always will have the state like this. So it's cosine 2k plus 1 over 2 theta defined on the previous page. And basically what we want to do is, as I said, get this state to be pointing sort of along this vertical direction, okay? So basically what we want is this thing to be 1 and this thing to be 0, right? Because then we'll have the maximum amount that's in the solution states and the minimum amount in the not solution states. So basically we need this thing to be 1. So we can just set this thing to pi over 2. You know, that's when sine is equal to 1. So 2k plus 1, 0, 2 is equal to pi over 2. Just rearrange this for, you know, k. That's the number of pairs of OV that you need to apply. And if you assume that n is quite large, which I guess, you know, that's typical case, then we can figure out that k is something like square root, because, you know, inverse sine you can approximate if the argument is small. Inverse sine is very similar to just a linear function. So k should be equal to pi over 4 times square root of n over m. Now, so finally got to the sort of the crunch point, I guess, of, so we've figured out how many times we need to apply OV to get our result. Now, the key thing is that we've got a square root here. So the number of times that we have to repeat our algorithm is actually square root of n over m. Okay. Now, let's go back to like basically what our original problem was. So remember what we're trying to do here in the first place is we're trying to search for something in the database. And actually maybe what I should have written here is that you know, I didn't really say how many solutions there were, but obviously if there's like more than one solution, then it's, you know, easy to find. Okay, so maybe what I should really say here is classically the amount of time that you need should scale something like n divided by m, right? Because n, because that's the size of the database, right? So if there's 14 entries in your database, then you probably need to look through at least half of it before you typically find the thing that you're looking for. But of course, if there's more than one answer, you know, like in this case where I'm looking for license numbers that end in 6, well, there's actually 2 of them, right? Now, if there's 2 of them, actually, you know, it's twice as likely that I find the correct case, right? So actually, you know, the more answers there are, the easier it is to find. So the quicker it is to find. So classically, the scaling of this search problem is like n over m. Now, if we compare that to our quantum algorithm, well, so it's square root of n over m, okay? And pi over 4, okay, that's 0.7 or something, so don't worry about it too much. Square root of n over m. So this is definitely a quantum speedup because, well, classically, there's really no other way of doing it. And the only way to do it is to really search through all of them. So that scales like n over m. But so quantumly, it's square root of n over m. So, you know, it might sound not so impressive, like square root of factor divided by no square root, but it can be significant because the bigger your n is, actually, the more sort of power that you can sort of see that it has. So, for example, if n is like 10 to the 15, you know, I mean, this is like, giga is 10 to the 12, right? So 15 is like tera, right? So, typical kind of computer sizes of everything that we deal with these days is, like giga or tera, right? So, your hard disk might be terabytes, processor speed is like gigahertz and so forth. So, like we live in a world where giga and tera are sort of typical numbers. So that's why I chose 15 like tera. So, that's a fairly big database. Right? Searching through it, it might take a bit of time. So, something with 10 to the 15 entries, which is 2 to the power of 50, might be, a realistic kind of problem size. But if it's a square root of that, that's only 10 to the 7. Okay, and 10 to the 7 is, just something it's like mega or 10 mega something, right? 10 megabytes or something like this. These days, transferring mega something is, pretty easy. So, it can make a big difference. Obviously, if these numbers are even bigger, then the speed up factor is kind of bigger. Right? Another thing is that it's very versatile. So, because searching is such a generic problem, like you search in all kinds of contexts. Well, obviously we search stuff on the internet, but probably more actually relevant is things like optimization problems. So in all kinds of areas of science, engineering, you often are always wanting to optimize things, right? So there's some variables and you want to find like the best parameters for it. So, this is potentially applicable to such situations. So I do mention that. So, even though this is very applicable, it's not always a clear winner because there's also, many good classical kind of heuristic algorithms. So, if you say that basically this is going to be faster than, anything, if you built a quantum computer, then this would be definitely faster. I think it would be still a case-by-case basis. So I think you couldn't always claim that this is always going to make any kind of computation like involving optimization faster because it really depends upon the problem. But it's, potentially something you can apply it to a lot of cases. And hold on, is this the last slide? Yes. So finally, I think the last thing is maybe a question that you might have had is to say, okay, well, how do I know how many times I'm supposed to apply this OV? Because obviously you don't know the solutions. You're looking for the solutions. That's the whole problem. How do I know how many times? Because if you don't know anything about solutions, then you also might not know anything about the number of solutions. You probably know something about the database size because that's basically related to the number of qubits. But the number of solutions might be actually unknown. So what do you do in that case? Well, there's actually some quantum algorithms that can actually allow you to estimate M. So actually, this can be done. I'm not going to really describe it, but there are certain things called quantum counting, so that you can know what actually M is, and then in that way you can actually figure out, well, know in advance how many times you've got to apply this OV sequence. Okay, so I think that's all. Any questions you guys have?
I have a question. Like in the phase flip, when doing phase flip, it's like reversing the first sign, but in the graph you've shown, it was like flipping like the like flipping the other, like if you like do the like the rotation around the plus states, and
Mm.
it wasn't like adding a minus sign in front of the plus state, but
Yeah,
on
so
the
I think, yeah, maybe, so I think maybe, let me try to just rephrase your question just to see if I got it right. So I think maybe what you're saying is that, so according to this, then the axes that you rotate around is, so if the oracle applies a minus sign to the solution state, then basically the axis that you go around is the other one, right?
Yeah.
Not solution. So by that logic, the V, which applies the minus sign to the plus state, should actually rotate around this perpendicular state and not the plus state as I drew here. Is this your question?
Yeah.
Yeah, I think you're right. But actually, in the end, I think it doesn't matter. Now, okay, the reason why I say I think it doesn't matter is that I could have defined this V state, and probably I should have done that so that it's clearer. So I could have defined this just with an overall minus sign everywhere. Okay, so I think I could have defined it like this. Okay, so with the plus sign on the V, and then and then a minus sign on the perpendicular. Okay, so if I defined it like that, I guess you wouldn't have had any problem, right?
Yeah.
But because this one is actually just minus of V, right? And
Yeah.
if you think about what this circuit is going to do, basically, if I just defined all these instead of V as, I think if I define as minus V everywhere, basically this just adds a global phase to everything, and I think eventually it really doesn't matter. Okay, so that's why I think it actually shouldn't matter. But then geometrically, why would this be actually the same? It's kind of a good question. I think I might have to sit down and think about it. So yeah, I can't see geometrically why, but I mean I think it should be basically the same. But geometrically, it's actually hard to picture. Yeah. Yeah, okay. Yeah, so that's a good question. Probably I should have just defined it the other way, and then there would be no confusion. Okay. But
Yeah.
yeah,
I think in
mhm.
this way, like we can always define it as the way we want to, like, to better show in geometrically.
Yeah.
Can always define it in that.
Yes. Yeah, okay. Minus sign. Yeah. Yeah. Yeah, I mean, another way to put it is that, basically this thing is a lot like, like a Z operator, right? So, here's like, remember our Z operator basically applies 1 to one side and then 0, sorry, applies a -1 phase to one state and then a 1 phase to the other one. Now, minus Z, of course, just does it the other way around. So -1, 1. But again, this is just a global phase. And what I guess should really matter is, you know, only this relative phase that actually that you have between them. So yeah. Or perhaps even geometrically, would this still actually work? So let me just, well, you know, I don't want to spend too much time doing it. So for example, over here, suppose that, okay, so first step, we rotate around this not sol, okay? And then suppose actually, you know, maybe to be perfectly consistent, I should actually reflect around this axis. Maybe I'll use green here. Around this axis, right? Then basically what will happen is that this vector will end up this way. I think it ends up pointing exactly the opposite direction to the original vector, okay? And then I think if it points exactly in the opposite direction to the original vector, it is, again, just the only different thing about it is that it's a global phase. And then I think actually there's no difference. But probably if you actually did this and then continued with the sequence where, again, all right, now so here's what happens after the first step, right? Yeah, yeah, and then the second step now it reflects around this axis, so it ends up here, and then finally we reflect around this axis, so it goes from here to here, and then here. I think we'll probably get the same answer. Yeah, so probably somehow after 2 steps, the minus signs will cancel, and we'll actually end up with the same thing. Yeah. So I think it actually probably doesn't matter which one you actually do. In the picture, it looks a little bit different, but then eventually it will still reach the same direction. And then after two rounds of OVs, then the minus signs cancel, and then there really is no difference. Okay.
Yeah.
All right. Okay, but that's a good question. Any other questions? Okay, it's basically time now. So maybe we'll finish up there. So in the next lecture, do you guys want to do revision? Maybe you probably do.
Yes.
Yes. Okay. All right. So maybe we should, you know, basically say that this will be the last lecture in terms of new content. And then in the next, on Thursday, we can just revise things and just go through any topics that you felt like you want to understand more. So yeah, maybe you can come prepared with topics that you want to cover. Okay. Right. All right. So we'll leave it there. And well, see you on Thursday.
Professor.
Yeah.
Okay. Bye.